5 minutes late, so the talk will be ending 5 minutes late too. So you'll get the full 40 minutes. So the speaker of this, the next speaker is Eran Palti from Ben Gurion. And the title of his talk is Stability of BPS States at Weak Coupling. So please.
Okay, thank you, Rossi. And thank you very much to the organizers for the opportunity to speak. It's a great pleasure. And what's a very interesting workshop so far. And I'm sorry to everybody which is quite late now.
Mariana can lower her hand, I suppose.
Okay, sorry.
Yeah, if you have
you
a question,
can lower your hand, I think.
Yeah, you can just speak out if you have a question, just shout out. Okay, so this is the title of my talk is Stability of BPS States at Weak Coupling. And it's based on a paper that came out 5 months or so ago. And some results that, yeah, I don't know really what to make of them. Maybe they're trivial, maybe they're not, I don't know, but I'll report it anyway. Okay, so one expectation that comes out of the Swampland program is that if a theory has a U1 gauge symmetry with a gauge coupling G, then in the G goes to zero limit, an infinite tower of charged states with increasing charges should become light relative to the Planck mass. So we should have some charged states with some increasing charge Q. G is a gauge coupling whose mass behaves something like this. And this goes back to the original proposal and has been tested and developed many times already. So I'm kind of concerned with this tower of light charge states. And one situation where you can test this idea is in a controlled setting is type 2B string theory compactifications on Calabi-Yau threefolds, which yield a 4-dimensional n equals 2 supergravity. And this supergravity has U1 gauge symmetries that come from the Riemann-Roman sector. And the gauge coupling of these U1 symmetries is controlled by the complex structure moduli of the Calabi-Yau. The states that are charged under these U1 symmetries are D3 branes that wrap 3 cycles in the Calabi-Yau. And the same complex structure moduli which control the gauge coupling also control the volume of these 3 cycles, and so the mass of these D3 branes. And so you would expect a natural, according to the conjecture, some correlation between the mass of these wrapped D3 branes and the gauge coupling of the U1 symmetries. And in this talk, I'll focus on a particular set of wrapped D3 branes, those which lead to supersymmetric states, so those which lead to BPS states. And mathematically, you would say that the D3 brane is wrapping a special Lagrangian submanifold of the Calabi-Yau. Okay, and it was shown that approaching any weak coupling limit in this Calabi-Yau moduli, complex structure moduli space, these BPS states indeed have a mass which behaves like the gauge coupling, and in particular is also exponentially small in the proper distance in moduli space. More precisely, what was shown is that a BPS state of those charges would have such a mass. But what was not shown, and what is an open question still, is are those charges actually populated by BPS states? So the central by BPS states. So we don't actually know the spectrum of BPS states in the theory, but that's actually a very difficult problem. In fact, the spectrum of BPS states is not known on any compact Calabi-Yau yet. So that's one of the things we're going to try and address in this talk. It's one of the things we want to think about. And another thing is that even though the BPS states never become the lightest in any controlled supergravity regime, it was proposed that they do offer a dual description of some of the string physics, specifically the infinite distance in moduli space, as well as the moduli and gauge fields themselves. This is a so-called emergence proposal. And the idea is that the infrared physics, the moduli space, is something that arises when you integrate out these D3 branes, or if you like, they are dual to each other, and there's an infrared duality between the moduli space and the D3 branes, the BPS states. So that's what the emergence proposal is called. So if such a duality is correct, then you would expect some correspondence between properties of the complex structure moduli space and properties of BPS states on that space. And then a very famous and simple classic example is the conifold singularity. So there is a singularity in the complex structure moduli space of the Calabi-Yau. And you can have a dual description of that singularity in terms of integrating out the BPS state, a D3 brane wrapping the 3 cycle shrinks to 0 at the location of the singularity. And note that this is really a dual description in the sense that if you integrate out the BPS states, then you have a singularity, but you don't have a singularity and the BPS state in that sense at the same time. So in this work, what I tried to do is make some steps towards making such connections between properties of the moduli space and properties of BPS states, but now not for this finite distance singularity like a conifold, but for the infinite distance singularities or infinite distance regions of the field space, which are the G goes to 0 recoupling limit of the complex structure moduli space. And that's the motivation I had, but the results stand for themselves for those who are interested in properties of BPS states and black holes in general. So if you're just interested in BPS states and black holes, and then that's interesting in yourselves, but this is the underlying motivation. So this is what I want to try and develop. So are there any questions? It's very abstract so far, so probably no, but if there are any, please go ahead. Okay, so if there's no questions, let's talk a little bit about what these BPS states are. So the mass of a D3 brane BPS state behaves like this. Well, it's there's only one dimension full scale on the problem, it's the string scale. It's a D brane, so it goes like one of the string coupling, and then it goes like the volume of the 3 cycle that a D3 brane wraps in string units. And you can rewrite this volume of the 3 cycle in terms of the volume of the square root of the volume of the Calabi-Yau, and then times some function, which is a function of the complex structure moduli only. And then you can combine these 3 quantities into the 4-dimensional Planck scale. And so the mass is just this function of the complex structure moduli times the Planck mass. And this function is called the central charge. The central charge, there's an expression for it. It's given in this form. So there is some constant symplectic vector eta. And then there is this charge, which is the charge of the D3 state. So you can think of this charge vector as either the charge vector of the D3 of the particle in 4D supergravity under all the U1s in the theory, or geometrically you can think of it as the wrapping number of the D3 brane on the 3 cycles in the Calabi-Yau. So that gives that specifies a particular D3 brane, or would-be D3 brane. So a would-be BPS state of that charge. We don't know yet if it's actually in the spectrum or not. And then pi is a so-called period vector. That's a vector which is a function of the complex structure moduli. So this is what controls the mass of the D3 branes as you vary the complex structure moduli. And then there's this Kähler potential prefactor, which is just this given by this logarithm of this inner product of the period vector itself. So that's the D3 brane states that we're going to be interested in. And note that these states are never lighter than string states in any supergravity regime because, well, a string state would have a mass ms. If you're in a weak coupling, then these would have to be bigger. And if you're in a volume which is bigger than a string scale, these will be heavier than the string states. So they are not the lightest states in the theory, at least not in any supergravity. And this is consistent with this emergent string conjecture, that the lightest state should always be a string. Note also, if you go to strong coupling, you can't make them lighter because then you would just get a D1 string being lighter than them. But you could make them lighter if you're brave enough and set the volume in string units to 0. And there might be reasons to believe that this is not so crazy because of the factorization of the moduli spaces, but I won't go into that. In the supergravity regimes, they're not lighter than the string states. So then the kind of duality I'll be talking about is not the typical kind of duality we get new light states. But they are the lightest charge states. So they are the only states that are relevant for things like the gauge fields and singularities on the moduli space. And in that sense, it's a control setting. So are there any questions about the BPS states and what's going on? Okay, so that's it. Yeah, so now an interesting thing is that upon varying the gauge couplings or the moduli fields, the BPS states can decay or combine. So if there is a state at some point, some value of the gauge coupling, in a spectrum, it doesn't mean that that state would be in the spectrum at some other value of the gauge coupling. They change as you vary the gauge coupling. And this occurs along codimension 1 loci moduli space called walls of marginal stability, where the triangle inequality is saturated. That just means that if you have a decay from one state A to two other states B and C, let's say, so you have charge conservation, and because the central charge is linear, you have this equation for the central charges. And then if you write the central charge as the mass of the state, which it is, times some phase, then the wall of marginal stability for this decay is just when the phases of these two constituents are equal. When that is true, then a decay is possible energetically, and it can occur. Whether it occurs or not depends on which states are in the spectrum. And there is a formula which tells you how the BPS states change, how the number of BPS states, or the BPS index changes as you cross these walls of marginal stability. This is the Kontsevich-Soberman formula. It's quite complicated, but you can see perhaps in the simpler primitive version of it, pretty much the physics that you need to see. So if you cross the wall of marginal stability, the change in the number of BPS states of charge A is just given by this formula, where here you have the symplectic inner product between the decay products, and then by the number of each of these decay products. And there's a simple way to understand that in terms of just strings stretching between the branes, and then the branes combining with each other or not. So this is the stability of BPS states. And so one of the interesting things people want to understand is how does the spectrum of BPS change as you cross these walls of marginal stability? And this is relevant for the Swampland distance conjecture, because we want to know if the BPS states are there in the spectrum or not at infinite distance. So I said that we're looking for some kind of duality or some kind of relation between BPS states on one hand and the moduli space on the other hand. So let me talk now a bit about the moduli space. So the moduli space is controlled by so-called monodromy loci. So these are loci on the moduli space where if you go around them, the period vector undergoes a monodromy by some integer matrix T. This is an example of a one parameter Calabi-Yau. It will have some of these kind of loci. So this would be the conifold locus, for example. This can be the large complex structure locus, and there may be some other infinite distance monodromy loci. And the moduli space is controlled by these monodromies in the following sense. If you write the monodromy matrix as e to the n of some other matrix, then the period vector, which gives you the geometry of the moduli space, is given by this expression here. This is the so-called nilpotent orbit theorem. It tells you that the period vector is given by this matrix n times log of z, where z equals 0 is the monodromy locus. And then there's an expansion here in positive, so in holomorphic expansion in z. So that means that when z goes to 0, if we switch coordinates t equals log z, let's say, then these are exponentially suppressed corrections to these leading terms. And when there is such a good expansion, so when these corrections are small, exponentially small, that means that we are in the nilpotent orbit regime. Physically, what this means is that you can understand these higher order z terms as instanton corrections, and being weakly coupled means the instantons can be dropped. So I'm going to be considering regions in moduli space where the instanton expansion is under good control. So that's what I call weakly coupled regions. So regions where the nilpotent orbit expansion makes sense. So somewhere near these loci. And of course, it becomes better and better as you go towards infinite distance. So at infinite distance, the infinite distance g goes to 0 limit is controlled by the nilpotency of n. In particular, you have this A0 coefficient here. If you have some integer d, such that n to the d plus 1 on A is 0, but n to the d on A0 is non-zero, then if d is 1 or greater, then this locus is infinite distance in moduli space. And that means g goes to 0. If d is less than 1, it's finite distance. And that's basically it. So there's d can and most be 3. So there's 3 types of infinite distance loci in moduli space, n equals 1, 2, or 3, d equals 1, 2, or 3. And each of those have the gauge coupling going to 0. Are there any questions so far? Okay, so now comes the relation, the result of the work essentially, where I'm going to relate this integer matrix n to some properties of BPS states. So n determines the moduli space, and I'm going to relate it to some properties of BPS states. the thing that one has is that n determines what's called, n is an integer matrix which acts on BPS charges in a natural way, and it determines what's called a monodromy weight filtration. So what that means is that if you look at the charge space of BPS states, it splits into certain subspaces which form a filtration. So one includes the other ones before it. If you want, you can define them precisely in this way through the images and kernels of n, but this is basically the picture you get. So if you think of the space of charges of BPS states, then it splits into 7 subspaces, and each one includes the previous one plus some additional ones. So this would be some set of branes, some set of charges. This space would have that set of charges plus one more, and so on and so on. And so it forms a filtration in this way. And when you act on the states in this till you get to the full space, n is a map which jumps between these subspaces, and it defines this splitting for you. And this is what's called a monodromy weight filtration. Very naively, intuitively, if the locus, the monodromy locus is the large volume regime of type 2a, let's say the mirror in type 2a, then these would be like D0, D2, D4, and D6 branes. But more generally, this is the actual completely general split that you find for any infinite distance locus. That means any weak coupling locus, the BPS states form this filtration of charges. Are there any questions about this? Okay, so then it's easy so now I can just state the result of the work. And so this is what I found, is that within any nilpotent orbit approximation of the moduli space, so that means whenever this instanton expansion is under good control, that's what I would call a weakly coupled region, a BPS state can only decay to constituents which do not have a higher weight in the monodromy weight filtration. So what does that mean? It means that you take your BPS states and you can split them into these groups, which are drew with different colored lines, and the weight is increasing in this way. So a gray, a charge which is in this gray line is bigger weight than a charge which is in this red line, and decays of BPS states across walls of marginal stability in any weak coupled region must go in this way only. So you cannot have a red state decay into a gray one, for example. That is the result, and that is a map. So I should say this is proven for so-called D equals one parameter infinite distance limits, but there is strong evidence that it holds generally, and I can discuss that. Okay, and the weight this is not so important. So this is essentially the result of this relation between the complex structure moduli space and BPS states. The claim is that an infinite distance G goes to zero limit in complex structure moduli states is an ordering or filtration of BPS stability on the BPS states. And the map is precisely what I said, that the monodromy matrix defines the monodromy weight filtration, and you only have decays of BPS states in one direction. So if you like to think of a decay of a state as decaying to something more fundamental, you would say that in any such region, these lower weight states are more fundamental, so they cannot decay to the higher weight states. So let me give an example to see what this means. This is a very simple example. So if you have a D equals 1 locus, then these two subspaces, then you only have 2 such subspaces, not 7. And these would just be what we call electric and magnetic states. More precisely, there are electric states and ionic states, since it's a filtration. So one space includes the other. So, and the mass of electric states goes like G times the electric charge, and the mass of a dionic state goes like 1 over G times the dionic charge. And so for this particular limit, what does the result tell you? It tells you that anywhere in this weakly coupled region, you cannot have a wall of marginal stability where an electric state decays to 2 dionic states. So you cannot have an electric state decaying to 2 dions. That's the result, that's the claim. And at first sight, this might seem a little bit trivial, because you would say, well, okay, if G is small, then the dions are very heavy and the electric state is very light. So how can an electric state decay to a dionic state if it's much heavier? But the point is that this is true for any electric charge. So in fact, this electric state could even be a supermassive black hole, the mass of our galaxy, of the black hole in the center of our galaxy. Still, it will not be able to decay to a dion. So it will not be able to emit a dion. That's the claim. And this decay is allowed in the sense that it's allowed by mass conservation. There are walls of marginal stability for such decays. So if you flow along the weak coupling towards weak coupling, electric states do cross walls of marginal stability to decay to dions. But the claim is that the spectrum of dions in the theory is such that there is never, those constituents of the would-be dions that it would decay to will never be in the spectrum of BPS states.
Eran, may I ask some question? I'm sure I'm confused, but I just was confused. So I thought that the formula for world of marginal stability is about BPS states. And so this supermassive black hole you are referring to is a highly non-BPS. So I wonder why you can make statement about its decay.
No, I mean, you can have an arbitrarily massive BPS black hole. Why not?
Oh, that was what you were thinking about. Ah, okay.
Yeah. So you can imagine a BPS black hole of the mass of our galaxy, and the claim is that that cannot emit a dion, which is of a Planck mass.
Ah, okay. Now I understand. Thank you. I was just
trying to explain that you might think this is a very naive, this is a very trivial formula because electric states are lighter than dionic states at weak coupling, but that's not true because you can have a very, very massive electric state. Because you can make the charge very massive.
Yeah, I guess so. I suppose in that case, QD is also very large. So,
sorry?
In that case, QD is also very large, right?
Yes, but the fact, this is what I tried to explain, that mass and charge conservation do allow the decay.
Oh, okay.
So it's not something that's forbidden by mass and charge.
Yeah, so it's not as trivial as that. Yeah.
No, yeah. Otherwise,
all right. Thank you. Sorry to interrupt you.
Yeah. No, in fact, I set out in the project to try and show such decays exist and then found they didn't. So yeah, it's not as trivial as that. It's something to do with the spectrum of states in the theory. It's not something that there are walls of marginal stability. They do cross them. And there is mass and charge conservation, but the spectrum of states, the population of BPS states is such that these decays do not occur. That's the claim. Thank you for the questions. Any more questions? And this is, of course, one example, but the statement is completely general, the one I made before, that there is a monodromy weight filtration and you cannot decay to something which has a higher weight. So this is the claim, yes. So, and you can say that one way you think about it is the fundamentality of states is determined by the mass at G equals 0, not at any finite G. So if you go back to the dion story, the black hole could be more massive than a dion at any finite G by making Q very large. But when G goes to 0, when G is 0, all dions are heavier than black holes. Even if you started with a very massive black hole and a dion which is lighter, always they will win. So in some sense, the claim is that in any weakly coupled regime, stability of BPS state is determined by G equals 0. And that's it. So you cannot have a state decaying to something which is heavier than it at G equals 0. So this is basically similar to these ideas of moduli space holography, which is telling us that somehow the spectrum or the moduli space is determined by the infinite distance singularity completely. Let me also explain something that follows from this, from what I just said. If you have BPS electrically charged black holes in the theory, if they exist, this is a non-trivial requirement because attractor flows diverge for electric BPS black holes. So they would have to be regulated by some string loop corrections and things like this. But if electric BPS black holes exist in the theory, then this guarantees for you that the light tower state is populated by BPS states. And in fact, the light tower states are exactly the black hole microstates. The multiplicity remains exactly the same because the electric black holes cannot cross any walls of marginal stability. I mean, they do cross them, but they cannot decay to any other states in the theory. So that means that electrically charged BPS black holes in any weakly coupled regime of supergravity are completely stable throughout the transition from GQ much bigger than 1, where their mass is much bigger than a Planck scale. So that means they're like a black hole. And then you can vary G to 0, and they become much smaller than the Planck scale. And throughout this whole transition, they lose no states because they cannot decay. The BPS index cannot change. And therefore, the light tower of states that you get at G goes to 0, the states that are much less than the Planck scale, which if you went back with G to finite G would have been black holes originally, they are populated, and they are just the black hole microstates because the black holes cannot have lost any states upon this transition because they cannot emit any dyons, and they cannot emit any electric charge states because when you cross the wall margin stability, it has to be with respect to a mutually non-local object. So are there any questions? That is basically the result of the work and the implications. And then the rest of the talk is about proving this claim that you cannot have an electric state decay into dionic ones. I'll wait 1 minute if there's any questions. Maybe
Maybe I can ask something, Eran?
Yes.
So can you, I mean, I understand this statement parametrically close to the infinite distance limit. Can you somehow keep track of, what happens if you go a bit away? Like, what is the number of stable states? Like, how the growth of the stable states change? You know what I mean? Like, if we go away from the symptotic limits, then we should be able to have those decays.
Yes, so the statement is that in any weak coupling limit, that means the instantons are small. All electric states, any electric state, no matter how big the charge, even a black hole, cannot decay as you go to G goes to 0.
But then there is no way to recover like some exponential growth for the number of stable states or something like that.
No, not that I mean, as far as I understand, they're just all, I mean, they're all stable, but it's not clear that they're all on the spectrum because eventually you go to black holes, and then when you have black holes, they back react on the geometry, and then you have an attractor mechanism, and the attractor diverges for an electrically charged black hole. So whether a BPS electric charged black hole exists in the theory or not is something non-trivial because you have to go beyond supergravity to work that out. So that could be where they're cut off. So I do not know if those states are populated or not, if the black holes are there. But if you have the black holes, then they stay stable all the way to become till they become much less than the Planck mass. They go through the whole Planck transition without losing any states. That's the claim. Okay, so any more questions about the results and the ideas? Okay, so here's the evidence and the proof for it. So there's two ways to see this result. One way is that you can use this correspondence in n equals to supergravity between BPS states and BPS black holes. And the idea is that if an attractor flow exists for a black hole of a given charge, then the BPS state of that charge exists in the spectrum. So this is a conjecture that was made by Moore and Denev, and I think it's probably correct. So I remind you that if you have a BPS charged black hole, then the scalar fields will flow to an attractor locus on its horizon. And if that point, that attractor point, is somewhere in the moduli space, it's a well-defined point in the moduli space, then that is a well-defined attractor flow. And if there is such a well-defined attractor flow, then you expect that state to be in the spectrum, where the point where it's in the spectrum is the value at infinity chosen by the value you choose for the moduli at infinity. In that correspondence, a decay across the wall of marginal stability means that you have a two-center black hole, such that the total charge is electric, but then when you flow, you split the attractor flow into two dionic centers. So in this correspondence, this is what a decay across the wall of marginal stability is, and this is the wall of marginal stability where this attractor flow splits. And then what you can show is the following result. If we call T log Z, and so T, the imaginary part of T being bigger than 0 means that you have a well-defined point in moduli space. And then this is the electric state, and you go to two dionic ones. You can show that the attractor locus of the two constituents, the two dionic constituents, that's the imaginary part of TB, TC, star means on the attractor locus, and the locus of the wall of marginal stability have to satisfy this inequality for this to occur. And this obviously can never happen if the imaginary parts are always big positive. So this can never be bigger than 1. So this can never satisfy. So that means such flows never exist. So you never have a flow to two multi-center ionic black holes which have a total electric charge. That's the claim. So that tells you that these kind of decays not exist, or if you like, the thing is that one of these attractor loci must be negative. So this suggests that one of these constituents must be absent from the spectrum, and that's why the decay cannot occur. And then you can further show that even if you try to, so if you say you have a flow and you go to a positive locus for this attractor, and this one goes towards this negative attractor locus, so that means it's a bad flow, and then you say, well, maybe it splits further and you go to a 3-center black hole, when these are all ionic states, the sum to an electric one, that you can show that this is not possible either. In other words, if you have an attractor flow that flows towards a negative value of the imagined part of T, then one of the constituents that it will split to will also have a negative value for its attractor locus. So negativeness of attractor locus is something that's conserved across splitting of attractor flows. That's the claim. And that's why you can never have anything like this. You can never have a decay. These things. So that's one way to understand it. There's another way to understand it. So this is showing that a decay which violates the filtration. So one where you start with an electric charge and you decay to two ionics cannot happen because at least one of the ionic objects cannot be in the spectrum. And this, we were seeing this by having a negative attractor locus. But you can see it a different way, which is perhaps easier to generalize. If you think about the following question, when does one of the decay products of the decay across the wall marginal stability have a vanishing mass? And you can solve that, and you can show that the vanishing mass locus is precisely the negative of the attractor locus. So having a negative attractor locus is the same as having a vanishing mass for one of these BPS, one of these decay constituents in a viable point in moduli space. So if imagined perturbation is negative for the attractor, then it's positive for the zero mass of the constituents. And what we were seeing before is that always one of the decay, one of the ionic black holes has a negative attractor locus. That means always one of those states has a zero mass in a good region of moduli space, in a positive value of T. And now, so this is what you find. You find that if you had some decay like this from some state that crosses a wall of marginal stability and decays to two constituents, B and C, if that decay violates this monodromy filtration, so in other words, this is, let's say, electric decaying to two ionic, then somewhere along this wall of marginal stability, one of the ionic constituents have to have a zero mass, will have a zero of its mass. That's what this result means. That's the same as saying there's a negative attractor locus for one of the constituent black holes. And now you can use the fact that we know that no BPS states become massless within the nilpotent orbit. There are no singularities in weak coupling apart from at infinity. But if there is a zero mass for a BPS state, it would have induced a singularity in the moduli space. So the absence of the singularities means that those states which have a zero mass must not be in the spectrum. It just must be, if the central charge vanishes, that state cannot be in the spectrum, otherwise you would have had a singularity in the space. Therefore, at least one of the constituents cannot be in the spectrum. This B cannot be in the spectrum because otherwise it would have induced a singularity in moduli space. And since it's not in the spectrum, you cannot have had this decay. And so you cannot have decays like this, electric states to two ionic states. Are there any questions about this?
Eran.
Yes?
Hello. I have a question about your supergravity argument of 2 slides.
This?
Okay.
Yes?
Yes, this one. So are you assuming that you are, within this perturbative regime everywhere in your solution?
Right. Yes, very good.
You need to assume it.
Yeah, so if you get a negative locus for one of these attractor loci, that tells you that you leave the perturbative regime at some point, basically, because it will flow towards zero and then you leave. So you cannot really deduce anything, but it's a hint saying that there is no well-defined attractor locus. The nice thing about the other argument is that now if you have something negative, it becomes positive, and that is in the perturbative regime. So here, there is no assumption. Here, you never leave the perturbative regime. So here you get better and better. G goes to zero along here, along this wall marginal stability. So in the supergravity argument, it's true. There is no solution because you leave the perturbative regime, but it's a hint that there is no attractor. The fact that there's no solution is telling you that there's some obstruction. And here you see it straight away without having to leave the perturbative regime.
Because I'm a bit confused because your moduli are the ones measured at infinity, no? Your black hole picture.
No. Here they flow. So
yes, they flow, but I mean okay. The modulus setting the mass and the charge of each constituent.
I'm not sure what the question was. Sorry.
So I'm a bit confused by the fact that here, yes, you are assigning some moduli to the horizon, I guess, the attractor point.
Yeah, so there is some point. There's an attractor locus for them. What is confusing about it? Sorry, I don't understand the question.
Yes, how you relate the attractor point value of the modulus to the modulus which you started from, that you change in the moduli space on which you put your you look for states.
This at infinity, you mean? Or yeah, this is not important. The point in infinity. The point is that there is some wall of marginal stability, which is this point with the locus splits. Okay, so what I've written here is a relation between this point in moduli space. That's this wall of marginal stability, and the two attractor loci of the two dynamic black holes. So that's the 3 points in moduli space. Where you start here makes no difference. And the claim is that this must be satisfied for such a solution to exist, and it can never be satisfied. So there is no such solution.
Okay, thank you.
Yeah, so this is the argument. Now, there is one way you could try to evade this argument as follows. Let's say you cross a wall of marginal stability, you decay to these constituents, then there is a zero somewhere else, but what if you crossed another wall of marginal stability with this constituent that has a zero here? We know they cannot be in the spectrum here, but maybe it was in the spectrum here and disappeared when you moved to this point here. So it crossed a wall of marginal stability along the way and decayed to some other constituents. But you can prove, just like before, that the negative attractor locus is conserved. The same thing is true here. If you have a state which has a zero along this wall of marginal stability and it decays to two other states, then one of those two other states must have a zero along its wall of marginal stability, and you recover again. So a zero on the wall of marginal stability in a good loci moduli space is something that's conserved by the decay. So you can never get away with it. Always, if this B was in the spectrum here, you will always get a singularity in the moduli space. So it cannot have been in the spectrum. And it's possible to show this result actually for any number of moduli in any D, the first one, the first result, this one. And it's very, very simple argument. The first thing you need to show is that the wall of marginal stability for a decay which violates the filtration, so something like electric to dionic, stretches all the way to G equals 0. And that you can show that. And now anywhere along that wall of marginal stability, we have an equality of the masses of the three states, of the state that decays to the two other ones. That's what defines the wall of marginal stability. And now this is what I said. If you have a state which is heavier than the constituents at some finite value of G, now go along G to G equals 0, one of these states will become heavier than it. But the diene would eventually become heavier than electric states. So at some point, their masses are equal. And when the masses are equal, this mass must be 0. So that's why you cannot change this ordering. You have a filtration. If you change the ordering along the wall, you will get a 0 in one of the masses of the states, and that means a singularity. And since there's no singularities, it cannot have been in the spectrum. So that's the argument. So basically, you cannot have a decay of something decaying to something else, which would become heavier than it at G equals 0. Even if at finite G, originally, the original object was heavier.
Eran, how many more minutes do you think you need?
I'm nearly finished. Well, that's the summary, essentially, yeah. So I'll summarize. Yeah, I'll ask if there's any questions about this kind of argument, or if there's no questions.
Okay, I'll ask later.
Okay, I'll summarize. So I gave evidence and proof in many cases, and I've actually been working on this and can generalize it, I think, to all cases. That BPS state satisfies stability filtration, which is determined by the monodromy about infinite distance, or the zero coupling limit. And this is consistent with this idea of emergence or duality, which is, and it gives some kind of quantitative connection between moduli space geometry and properties of BPS states. So much like in the conifold, the singularity is some relation between the geometry and BPS states. The claim is that this is the relation that's appropriate at infinite distance. So an infinite distance G goes to zero limit corresponds to an ordering or a filtration of BPS stability. That's what these two things correspond to each other. And it's interesting because stability of BPS states has a microscopic description. You can study it by studying certain quantum mechanics on their intersections, or you can study the string spectrum between the intersections. So it would be nice to try and understand what kind of physics leads to this ordering of filtration of BPS states, where things cannot decay to other things, and how this matches onto this infinite distance limit. And as I said, it's also a proof of the distance conjecture. So it proves that the BPS states are populated, at least if electric black holes exist in the theory. So if electric BPS black holes exist in a theory, then the BPS states at infinity are populated. And in fact, they are the black hole microstates of the would-be black holes. That's it. Thank you.
Thank you. So I take my position as a chair to ask the first question. I will take a few more questions. It seems like there are some. So I wanted to just ask whether this result is the gravity is important. So if you take the limit when Planck mass goes to zero, does infinity, then does this property disappear, or?
I don't think it does disappear. I mean, is this
a field theory statement?
As far as I can tell, yes, because this is such a simple argument. I'm not, wait. I'm not sure that in field theory, it's always the case that the wall margin splitter goes all the way to G to zero. I showed this for the supergravity expressions.
Right, yeah, so that was my confusion. So question is that, should I consider this as one of the Swampland property that disappears if you take the limit of field theory limit?
Yeah,
or is this also a field theory limit? Statement.
I do not know. I'd imagine it is tied to gravity because showing that the Waller margin stability, which violates this filtration, goes all the way to G equals zero, which is a crucial aspect of it. A crucial aspect of it is I'm not sure that's true if you don't have the supergravity has a 1 over the Kähler potential. The difference between supergravity and the gauge theory is
suppose, for example, you wrap D-branes and non-compact Calabi-Yau to construct some BPS state. Does this property hold for these guys?
I think it may hold as well, yeah. Because actually, it's actually related to some assumption that's made in the Kontsevich-Solbermann wall crossing formula, where they restrict to states which have no zero around the locus where they're going around. And this having no state which has a zero is something that's never been proven that's true in generally in field theories. So this is kind of related to this.
Okay.
But I think it's true, but I've not thought about it. It's a good question. I'll think about it.
Thank you. Okay, so let's take questions in the order that hand was raised. So start with Naomi.
Hi, thanks for the talk. I just had another question about the argument about the attractor flow. I probably just missed it, but can you explain again why an attractor flow where the imaginary part of T on the horizon becomes negative is necessarily a bad attractor flow? Couldn't it just enter maybe some new geometric regime or something?
Yeah, so this is the same question that Luca asked in some sense. It's not a good attractor flow, so you can say that. In principle, you can't say what happens because it will enter some strong coupling regime. If you can solve formally the equation and find that it goes to negative value, but what this means is not necessarily that it goes to negative value, because before you reach negative value, you will lose the perturbative control on your theory.
How do you say that it necessarily goes to a strong coupling regime?
Yeah, but what this shows is you cannot have a good attractor flow. So you cannot have this happening fully in the recoupled regime. So it doesn't prove that there is no such thing, but it proves that there's no such double center black hole where you stay in the perturbative regime at all times. But I think it gives you a correct answer because it precisely matches the zeros here. You see the attractor flow, minus the attractor flow is precisely the locus where there's a zero for the central charge. So if you say that a state which has a zero in the positive value of the moduli cannot be in the spectrum, which makes sense because if it did, it would have a singularity in a moduli space, and we know there's no singularities, then you see that it precisely tells you that a state which has a negative attractor flow doesn't make sense. And so this is the precise one-to-one correspondence. So the fact that you don't have good attractor flows, at least, is exactly the same so I believe this is capturing the correct physics. Yeah, but your point is correct. You cannot track a negative, a bad attractor flow. You cannot track past the weak coupling region. Yeah.
Thank you.
Okay, Timo.
Thank you, but I think was Alessandra not before me?
Okay.
I don't want
since
to
you already
jump
have your video
Go
on,
ahead.
why don't you ask question? I will give a chance to Alexandra too.
Go ahead, Timo.
Okay, thanks. Just a quick one. You may have already answered it, Eran, in your reply to Hiroshi's question. But so your statement that certain BPS states cannot decay into others, this is true for the set of all BPS states, and not only for the subset of BPS states which become light at infinite distance. Did I understand correctly?
No, that's for all BPS states. So even for massive BPS states decaying to other massive BPS states.
So also for those BPS states which would become light at finite distance, like at the conifold, the statement should hold.
Finite distance
only for those at...
No, this is at infinite distance, but you can. So let's say if you did, if you had this filtration, you could have, like, if this was a d equals 3 locus, then you would have these states becoming light, states here becoming light, but states here and states here would be massive. So like red or purple ones be massive, but even though they're not becoming light, they cannot decay backwards. So it's not just a statement about the states which become light, but in particular, it is a statement about the states which become light, which are of interest for us. So the states that become light will be like the states here, like the yellow ones or the blue ones, and they cannot decay backwards. So that means an electrostate cannot decay to a dion. But it's also true that these dions cannot decay to these other dions, even though they don't become light. Yeah. So you just get this whole filtration through the stability.
Thank you.
Yeah.
Okay, Alexandra. Thank you.
Thank you. I apologize if I missed this remark. In the n equal to 2 supergravity, one has electric magnetic duality. So I wonder, like, if you can rotate your arguments to a frame where there's also dionic states.
There are dionic states here. So, I mean, this is within a certain weakly coupled region. So you cannot invert the gauge coupling. I'm not sure exactly what.
Okay, so the duality transformation will be non-perturbative.
Yeah,
so it would.
Yeah, so
okay.
you can have between these different locus. So like a monodromy defines a certain region in moduli space, and what is weakly coupled in one can be strongly coupled in the other. So this locus would be strongly coupled with respect to this locus and the other way around. But I'm talking about what happens within a region where this locus is applicable, and you flow towards this G goes to 0. So you cannot do like a strong weak duality within that region.
Okay, so Irene?
Yeah, just very, very quick. So it's following Timo's comment. So at some finite distance singularities like the conifold, we still have this monodromy filtration. So maybe you can extend your results to apply in those cases, no?
Yeah, so I thought a bit about this, but it wasn't, I think it's probably true, but I'm not 100% sure. But in the case of the conifold, the only electric state is the one that becomes light. It says that the monodromy filtration in this, there's only two elements, and one element just has one state in it, which is just the conifold state, and there's no high multiples of it even. So you can't form a black hole to decay to a dion, if you see what I mean. So what I said was that generally electric states would be lighter than dions. But I said if you can take a very large charge, then you can have electric state being heavier than a dionic one. But in the case of a conifold, you can't take a large charge.